Earlier, we just learned about standing waves and strings. Well, we can get standing waves in other types of waves, sound waves. We'll look at standing waves in long, narrow columns of air, which produce longitudinal standing waves. Standing waves in sound are a little bit trickier to visualize than standing waves in string waves. Why? Well, let me show you a quick little animation of what a longitudinal standing wave or a longitudinal wave just looks like. So here we have a tube of air, and we have air particles that are in here. So if I start to oscillate this back and forth, you can see if I increase the frequency, now the wavelength shortens, and you can see the compressions and the rarefactions in this picture. So there's particles in here, and remember that when we have the particles that are really close together, we have a compression, and when the air particles are really far away from each other, it's called a rarefaction. So hopefully you realize from that animation that it's the displacement of the particles is parallel to the tube. They're moving along the same direction as the tube length. Now, in a standing wave for a sound wave, what is considered a node? Zero displacement. So if you take a look at the picture over here to the right, we have a one-end open pipe, or organ, or whatever you may be. You would press your lips normally here and blow in the air, and then the sound would be coming out this area right here. Now this end is closed. This closed end right here, the column of air particles here, the air particles right at this location are right pressed against the wall. They're not able to move. So that position right there is where the particles are not moving, and this is what we consider a displacement node. And at the opening right here, where we have labeled an A, that would be considered the antinode, where you would get maximum displacement of the sound wave. Now, if you play in an organ pipe or whatever, a wind instrument, where you have two ends open, this end is open and that end is open, then both openings here will have an antinode. And so we have maximum displacement occurring here with the air particles, and in the middle we would have to have a node. So how do we figure out how much of that sound wave, the wavelength here, corresponds to the length of this air column? The technique that we use to determine the relationship between the length of the air column and the wavelength is very similar to what I would use with standing waves and strings. So imagine you were shaking a rope up and down and making this nice sine wave here. And then there's a barrier right here so that the wave then would reflect. Remember that 180-degree phase change. And so it would make a perfectly second wave with the same amplitude, wavelength, and frequency. And this distance here is really just one entire sine wave. Remember this distance right here is lambda. So if we were looking at the situation where we have one end closed of our standing wave here, we know that we must have a node here. And then at the opening area, that must be an antinode. So we get this kind of pattern here. So this is really, you just need to look at kind of this wave over here. So it's just kind of this section that you're looking at, this section right in here. So how much of a wave is shown in there? Not perfectly shown in here, but you can see hopefully that you could break this whole wave into a quarter, a quarter, a quarter, and another quarter of a wave. So what you see really here at this first harmonic for a closed at one end situation, the length of this pipe L is equal to a quarter of the wave. So you can see this, it's highlighting here a quarter of one entire wave. Now, if you were to look at this scenario now, if it's open on both ends, we have an antinode at both openings. So we have an antinode and antinode here. In the middle of this pipe must be a node. So we're looking at this pattern here now. And so hopefully you can see that this center part of this wave here and here. And I hope that one would realize that this is really half of a wave. And then you can continue on. For example, over here, you have 3/4 of a wave. You see we have an antinode, node, antinode, and then node. And so now we're looking at really this section in here. And so I hope that you can see that this is 3/4 of a wave, and hence L is equal to 3/4 of a wave. So again, study the pattern rather than the equations. You can see in each of these scenarios. Now over here you have one entire wave. This is really just a cosine wave. So that's one entire wave. Now there is a difference that you see between the two scenarios. With both ends opening, you start off with half a wave, then a whole wave, and then continuing down here, you get 1.5 waves. This is very similar to strings, except at the end points we have antinodes. Now, with one end open, you start off with 1/4 of a wave, then you go to 3/4 of a wave, and then you go to 5/4 of a wave. So you're starting off with 1/4 of a wave. Now, you may notice something important here, that in both ends opening, you have F1 and F2, and then continuing on, you have the third harmonic. So you get every consecutive harmonic. But with one end open, something interesting happens here. You only have the first harmonic, and then you skip the second one, and you get the third, and then you skip the fourth one, and you go to the fifth. So you really only have the odd harmonics available. Okay, again, really it's just a pattern. If you can study the patterns that you get and understand the physics between the antinodes and the nodes, then you can determine what the relationship is between lambda and L, and then you just simply use your equation. Down below in the notes, you'll see I have some formulas written down for both ends open and one end open, but I think it's important not to memorize the formulas, to know how to use the equations. Spend time studying the patterns in here and figure out the relationship between L and lambda from the pattern that is shown, because that's what's likely going to happen. You'll get a picture and you have to look at the picture. They're not going to tell you it's the fifth harmonic, for example, necessarily. So V equals F lambda. That's really all you need to know, and then these diagrams. Okay, go ahead on to the next examples.